Hello, in this video we're going to discuss linearization, which is an approximation technique, and it uses the concept of functions in a local area around a point being roughly linear, almost no matter what the function is. If you have a sine curve, for example, and you know this point right here, if you want to approximate that point, you draw your tangent line. If this is the actual and that is the guess, you can see they're pretty close. If you go farther out, if you guess that point for this point, it's pretty terrible. But the idea is that within a certain little radius, within a short little radius, a function, no matter what, is pretty linear. If you did this with a parabola, say you know that point, that's x, and you draw your tangent line there, and you want to guess this point. This is the actual, and you go up to the tangent line to make this guess. The idea is that is a pretty good guess of that point. If you're closer, if that was a guess at that point, it's even better. So within a short little window around your curve, you can use a straight line, which we know a lot about straight lines, to guess the y value of a function that you may not know a lot about. So I'm going to kind of work through this with a square root function. We're going to just take the function square root of x, and I want to guess the square root of 27. I'm going to guess what that is. And we'll look at the comparison to the actual afterwards. But here's the idea. We're going to take a known starting point and say actual y, actually not actual yet, guess of y is approximately equal to a starting point that's known plus the change in y. And I'm going to call that delta y or dy. And to get dy, I'm just going to write it like this: dy over dx times dx, since those cancel out. The reason for writing it as dy over dx times dx is dy over dx is the derivative, and dx is the amount of change in the x direction. And these are two things that I can show with math. It's a little bit easier to think about than change in y. So we're going to kind of use that approach and do this. We're going to do f of 27 is approximately equal to a known starting point is f of 25. I know the square root of 25, so we'll start with that. Plus the derivative at 25 times the dx. The dx is how far we went from 25 to 27, and that's 2. So we'll just see what happens here. We need the f prime of 25 of the square root function. So I'm going to have f, this is x to the 1/2. So f prime of x is 1/2 x to the negative 1/2, which is 1 over 2 roots of x. So f of 25 is 5. The derivative is going to be 1 over 2 roots of 25 times 2. 5 times 2 is 1/10, times 2 is 1/5. So that's going to be 5.2. So my guess is 5.2. And let's just see the actual. Square root of 27, 5.196. We'll round it off to 5.196. So, not bad. If you want to make this better, what you can do is make the step size smaller. The closer you are to the original point, the better your approximation is going to be. And what you can do is do individual steps. So instead of going from 25 to 27, go from 25 to 26, and then go from 26 to 27. So let's do that. So this time we're going to approximate f of 26. And let me just write down what we saw a minute ago. That was my function. My derivative is 1 over 2 roots of x. So we're going to say f of 26 is approximately equal to f of 25 plus the derivative at 25, this time times 1, because the step size from 25 to 26 is 1. That's going to be 5 plus, if you put 25 in here, you get 5. 2 times 5 is a tenth, so you get 1/10 times 1. That is 5.1. Now we'll go f of 27 is about equal to f of 26 plus f prime of 26. I'm sorry, f prime of 26 times 1. So this is going to be, my guess of f of 26 was 5.1. The derivative was 1 over 2 roots of x. And we approximated f of 26. The square root of 26 is 5.1, so I'm going to put that down. Times 1. And so we get 5.1 plus 1 over 10.2. Let's see what that is. Plus 1 divided by 10.2. 5.198. And the actual, if you remember, was about, the equal sign was about 5.196. So you can see it's getting closer. The guess with the step of size 2 was 5.2. With 2 steps was 5.198. The actual is 5.196. If you did 4 iterations with a step size of a half, you would get a closer approximation. And ultimately, you can get an approximation as close as you want by doing many, many steps. So, this is an introduction to numerical approximations. A question that you're probably going to ask is, why would I ever want to approximate the square root of 27? Obviously, I use my calculator to figure this out anyway. I acknowledge that you're not going to, find the square root of 27 doing this. But this is a way for you to kind of have a window open to the world of approximation techniques. Yes, I can find the square root of 27 in my calculator, no problem at all. When you take differential equations, especially, you're going to find that there are problems that are either unsolvable or not easily solved. Your calculator won't do them, and you're going to have to rely on numerical approximation techniques to be your bread and butter and to get through those problems. So this, even though from a practical standpoint, it may not be something that you go out and use, it introduces you to the concept of what a numerical approximation technique is and how iterations can be used in these techniques. So think of this as practice for a more complicated and useful technique that you may have to use in the future.